So far the downlink and downlink related procedures. Let's look now at the uplink. As in a downlink, there are physical signals and physical channels. During explanation of the downlink HARC procedure, we already mentioned the two physical uplink channels. Physical uplink shared channel and physical uplink control channel. The other channel in the uplink is the physical random access channel, which carries the random access preamble and which one we discussed during explanations for the initial access procedure. The two types of the physical signals are the demodulation reference signals, which are used by the eNode B for channel estimation and correct demodulation. Further, sounding reference signals used by the eNode B to find scheduling decisions based on the channel quality. As said, data are sent by the UE on the physical uplink shared channel. This channel, again as the name implies, is shared between all UEs in the radio cell. That means the UEs are sharing the bandwidth of, for example, 20 MHz equals 100 resource blocks when the radio cell is configured for that bandwidth. A UE would get resource blocks are assigned where QPSK, 16 QAM or 64 QAM can be used as modulation schemes. Note that 64 QAM is an optional modulation scheme in the uplink. The question is how different UEs are scheduled when they would like to transmit their data. The scheduling is made by the network, better the eNode B. On the physical downlink control channel, a specific format, the downlink control information format number 0, is used to indicate to a UE on which resource blocks to transmit its data and which modulation encoding scheme to be used. Further, this format indicates to the UE if frequency hopping should be used or not. In LTE, there are two modes of hopping, intra and inter-subframe hopping. Hopping at all is an optional feature, but it is an approach to overcome possible frequency selective fading on the radio channel. When intra-subframe hopping is configured, the UE hops from one resource block allocation to another one within one subframe. This means at the one slot the UE would transmit, for example, on the lower edge of the spectrum, in the second slot on the upper part of the available spectrum. Inter-subframe hopping means now that the UE changed the allocation from one subframe to another one. For each hopping mode, two types of hopping can be configured. Type 1 defines an explicit frequency offset used between the two allocations. This is shown in the screenshots taken from Rohde & Schwarz leading vector signal generator SMU200A. With the SMU200A, a 3GPP compliant uplink signal is generated and two fixed frequency offsets between the allocation are configured and shown in the two screens. Type 2 uses a predefined hopping pattern where the available bandwidth, for example 20 MHz corresponding to 100 resource blocks, is split into subbands and the UE hops between those subbands. To ensure proper demodulation, demodulation reference signals are used in the uplink. In contrast to the reference signals used in the downlink, the demodulation reference signals are not transmitted on specific resource elements. Instead, the demodulation reference signal is transmitted over the entire allocated bandwidth and occupies a specific single carrier FDMA symbol. The screenshot shows the timeplan of Rohde & Schwarz vector signal generator SMU200A, generating a 3GPP compliant uplink signal. 11 resource blocks are occupied and frequency hopping type 1 is applied to the signal. We can see that the single carrier FDMA symbol number 3 in the first slot and symbol number 10 in the second slot carries the demodulation reference signal. If the UE would be assigned to transmit on less or more resource blocks, the demodulation reference signal would also be transmitted over these resource blocks. This is mandatory due to the nature of single carrier FDMA. The other physical signal in the uplink are sounding reference signals. Sounding reference signals are used by the base station to estimate the quality of the uplink channel, to be used as a basis for scheduling decisions, means where a UE should transmit its data. The eNode B is free in its decision to configure bandwidth occupied by the sounding reference signals, power level, etc. At this time, the UE knows where to transmit its data, which modulation encoding scheme to be used, if frequency hopping should be applied, and if there is a need to generate in addition sounding reference signals. Now it is important to know with which power level the UE should send its data. First of all, the UE calculates the power for the physical uplink shared channel based on this formula for every subframe, so every 1 millisecond. As it can be seen, the power level depends on various parameters, starting with the maximum allowed power, which depends on the power class. There is just one power class in LTE defined, defining plus 10 to 3 dBm as maximum power, which corresponds to the power class 3 in wideband CDMA. Next is that the number of resource blocks is important. A number of cell and UE specific parameter is taken into consideration, provided by higher layers, as well as the downlink path loss and the transport format. This information is derived within the DCI format number 0 on the physical downlink control channel, where also the transmit power control information is taken from. We looked here substitutional at the calculation of the power level for the physical uplink shared channel. The calculation for the physical uplink control channel, physical random access channel, and for the sounding reference signals based on similar formulas, and is also influenced by higher layers and cell-specific parameters. With all the information we discussed on the last slides, the UE is now ready to transmit. The question is now when the UE starts with its transmission. The timing relation between receiving all the information via the DCI format number 0 on the physical downlink control channel and start of the transmission is 4 subframes, so 4 milliseconds. After 4 milliseconds, the UE starts transmission on the physical uplink shared channel on the assigned resource blocks with the calculated power level. In TD-LTE, the timing relation is impacted by the used uplink downlink configuration, and there is at least a 4 millisecond subframe interval between receiving the physical downlink control channel and starting transmission on the physical uplink shared channel in the uplink subframe. Of course, also the UE would like to know if the data it has transmitted has been decoded correctly by the eNote B. To provide that feedback means sending ACNAC information, the eNote B set up another downlink control channel. This channel is the physical hybrid ARQ indicator channel. This channel carries the ACNAC information to the UE. We already run into this channel as we discussed the information transmitted via the master information block. The master information block carries duration information for the PHICH. The duration of the PHICH differs for LTE FDD and TD-LTE. The PHICH is always transmitted in the first symbol of each subframe in the downlink. The ACNAC information on the PHICH corresponds to the data packet sent in the uplink 4 milliseconds before. Last but not least, we need to discuss the physical uplink control channel, PUSCH. The PUSCH carries the uplink control information, means a scheduling request, ACNAC information, CQI values, and parameters like pre-coding matrix indicator or rank indicator, which are necessary for MIMO transmission. A physical uplink control channel is only issued by the UE when no uplink data transmission is ongoing. In that case, the user data and uplink control information is multiplexed onto the physical uplink shared channel. That means one UE is only issuing a physical uplink shared channel or a physical uplink control channel, never both. The physical uplink control channel is transmitted on reserved frequency regions, means the lower and upper edge of the available spectrum. This minimizes the effect of possible frequency selective fading affecting the radio channel. Further, interslot hopping is used for the PUSCH. That means the transmission jumps from, for example, the lower edge of the available bandwidth to the upper edge within one subframe. This is also to ensure that the uplink control information arrives at the eNote B. Depending on the information to be transmitted, different formats are used as shown in the table, using different modulation schemes and a different number of bits.